Okay, so good morning and welcome you all for this continuation of this hydraulic turbine class. See, yesterday we were looking at the expression for work done for a Pelton wheel. In that, we arrived at an expression for a specific work where W by M is given by V1 minus U into U plus 1 plus CB into cos beta 2, where CB is some kind of a friction factor. Now, let us try to find the how we can obtain this particular, how and what condition this work will be maximum. See, for the maximum or to obtain the maximum work done or condition for maximum work done, whatever it may be, the condition for maximum work done. So what I do actually, if you look into it actually here, what are the factors, what are the parameters we have? So we have U, V1, CB and beta 2. Okay, if I try to look into it, what are the factors which we have here is actually U, V1, CB and beta 2. So now if you look into this particular thing, so V1 control, because V1 is what the jet of velocity which will be arriving at your turbine, and friction factor is also constant. So now what will be the variable? The variable will be your speed. So if we want to maximize this actually, so what I'm going to do actually, I'm going to dW by du and equate it to 0. That's what I'm going to do. So if I do that, so this will be d by du. So into this will be, if I try to put it, v1 minus u, okay, into u within my bracket 1 plus cb into cos beta 2, okay, is equal to 0. So if I differentiate it actually, what is going to happen? See, 1 plus CB cos beta 2 automatically it will go off. So I am left with only, this will be only d by du into v1 into u minus u square. Okay. So the rest of the thing, if you multiply, I can take it to the right hand side and it will become 0. So now if I differentiate this actually, so differentiation of v1 u is actually, it is v1, and differentiation of u2 square, u square is equal to 2u is equal to 0. Or I can tell my u is equal to, if I take it to the other side of it, it will be v1 by 2. Okay. Or for a maximum condition, my u is 50% of your v1. So this is the condition. So what I'm going to do, substitute the u value. So substitute this condition. So substitute the value of u in equation 7. So then what I'm going to get actually, it is W max is equal to, so if I substitute, first it will be V1 minus 1 upon, that is half V1. Wherever U is there, I'm going to put half V1 into half V1 into 1 plus CB into cos beta 2. Okay. Now if I take V1 outside, so this will become V1 square. Okay. So V1 square, 1 minus half is half, half into half, it is 0.25 or 1 by 4. Okay. So this will be V1 square by 4 into 1 plus CB into cos beta 2. Okay. Or I can tell that W max is equal to 1/4 of V1 square into CB into cos beta 2. So this is the expression for your maximum work done. So now under this condition, suppose if my CB is equal to 1, okay, and your beta is equal to, beta 2 is equal to 90. Say some condition. If beta 2 is equal to 90, your cos beta is cos 90 is 0. Fine. In that case, it will be only V1 square. So, for different conditions, I can substitute and get the value for your W max. So, your V1, so beta 2 can be any number between from 0 to 180. So, it can be 0 to 90 or 90 to 180, whatever it is, or it can be 190 also. And CB value, so if there is no friction at all, then I can tell V1 and VR1 and VR2 both are same. So in that case, CB is equal to 1. So this will be, for CB is equal to 1, the W max will be V1 square by 4 into 1 plus cos beta 2. That may be condition. See, I told that yesterday, we have one condition, what is called as speed ratio. Because whenever we are trying to solve the problem under Pelton wheel, so this particular speed ratio, they try to give in the numericals. So what is the speed ratio? Speed ratio, okay, it is denoted by phi. It is a ratio of your blade speed to your jet, or what we call it as your absolute velocity. Or I can tell u is equal to phi into v1. Okay, u is equal to phi into v1. So wherever this particular, what I want to do, I am going to take this expression 7, I'll substitute for u in terms of v1. So I can write w by m is equal to v1 minus phi into, so this expression, I am speaking of this expression. I can write, wherever u is there, I will write in terms of v1, that is pi into v1, so that I can write the same expression in terms of specific, or what we call it as speed ratio. If I do that, so let me take that expression. Therefore, equation 7 becomes, I can write it as w by m, or w is equal to v1 minus phi into v1 into phi into v1 into 1 plus cv into cos beta 2. Or I can write your w is equal to, if I take my phi outside, so phi into, so v1 square I can take it out. So phi into v1 square, if I take it out, this will be 1 minus phi into 1 plus cb into cos beta 2. Let me call this as expression number 10. So this is the expression in terms of phi and v1 and here. So here also I can have a condition where cb is equal to 1. So I'll be getting in terms of w is equal to phi into v1 square into 1 minus phi into 1 plus cos beta 2. I can write an expression for this also. So I can substitute for, here also I can maximize it. If I want to maximize it, I can write in terms of dw by d phi. I can do that. So that also, but usually we try to maximize with respect to u. So this will be the expression for the equation 9 is the expression for maximum work done, and w is the equation 10 is the expression for work done in terms of speed ratio, blade angle, and your whatever called friction, that is cb or k, whatever it was. So these are the expressions what we have to look at for your Pelton wheel. Now, so we have to look into the what are the efficiencies associated with Pelton wheel. Okay, let's look into the efficiencies associated with Pelton wheel. Efficiencies associated with Pelton wheel. So the first efficiency that comes to our mind is actually, it is your hydraulic or blade or vane efficiency. All are same. So few books represented by vane efficiency, few books they call it as hydraulic efficiency, few books they call it as your blade efficiency. So what is it actually? It is nothing but your hydraulic efficiency. It is defined as, it is a ratio of what is the energy that is converted. So energy that is converted, your work done. So energy converted by the fluid that is your work done to, okay, energy available with the fluid, that is with water, okay, energy available with the water, that is fluid with the water. Or what is your work done actually, I can write in terms of your Euler equation. So I can write it as, this is VW1 minus VW2, okay, into U. Then what is the energy available with the fluid? It is omega Q H. See, what is the H actually? You have to be very careful here. This H is nothing but your net head. So never ever substitute the gross head. Okay, never ever substitute in gross head actually. It should be net head. And also, so this equation will become VW under this condition. This will become VW1 plus VW2 into U if minus VW2. That is, it is in opposite direction, not that condition. So this particular equation, no, this will become like that. I'm writing both actually. VW1 minus VW2 into U with the general Euler equation. If my minus VW2 is there, then that will become VW1 plus VW2 into U. Now same expression. Suppose this is pure kinetic energy. So what is the energy available? It's pure kinetic energy. Instead of writing in terms of omega QH, we try to write the same expression in terms of, okay, we try to write the same expression in terms of VW1 minus VW2 into U divided by your V1 square by 2. This is your pure kinetic energy. This is under condition where it is a pure impulse turbine. Okay, we try to write it as a pure kinetic energy. If I try to express the same thing in terms of kinetic energy, or if I want to express in terms of discharge and head, I'm going to get what is called as that particular energy, which is omega QH. So this is the first efficiency. The second efficiency is your volumetric efficiency. The second efficiency is your volumetric efficiency. Okay, what is this volumetric efficiency? It is nothing but amount of fluid striking the blade or vane. Okay, amount of or quantity. Let me write it in a different fashion. So rather call it amount. Let me call it as quantity of fluid, quantity of water striking the blade or vane. Okay, what is the amount that is striking the blade to amount of fluid entering the turbine? Okay, if I try to take the ratio of it, so the quantity of water entering the turbine, or what is available at the entry and what is that is striking the blade, there will be some loss. If I try to write in terms of discharge, because I am trying to deal with the water which is an incompressible fluid, I try to express the same thing in terms of discharge. So this will become Q minus, that is the loss, that is delta Q divided by Q. Or, so very rarely we try to express in terms of mass flow rate. That is mass flow rate minus what is the loss of fluid. So this is how your volumetric efficiency is expressed in terms of discharge. Majority of the time we try to express in terms of discharge because this being an incompressible fluid. Okay. Third efficiency, mechanical efficiency. Mechanical efficiency. What is it actually? Energy that is available at the shaft to the energy that is available at the rotor or work done. Okay, that is your mechanical efficiency is equal to energy available at the shaft. Okay, that is the energy that is going to the generators. Okay, that is energy that may be going to for power generation, whatever it may be. Energy available with the shaft to your energy available at the rotor. At the rotor, this is actually your work done by your fluid. So what is it actually? It's the Euler work done. So energy available at the shaft is actually, this is the shaft power. We call it as P shaft. Here it is energy available. This is actually VW1 minus VW2 into U. So this is my mechanical efficiency. The last efficiency, okay, the last type of efficiency is your what is called as overall efficiency. The fourth one, that is fourth one, overall efficiency. Overall efficiency. What is it actually? It is the energy available at the shaft. So this is nothing but overall efficiency is nothing but energy available at the shaft. At the shaft to, okay, energy available, that is energy supplied by the fluid, or energy supplied or energy available with the water. Okay, energy available with the water. With the water. If I try to write it, actually this is P shaft to omega QH. Okay, P shaft to omega QH. Or maybe most of the books, what is overall efficiency? Most of the books they write it as, so overall efficiency is equal to, it is a product of your all your efficiency, the hydraulic efficiency, your volumetric efficiency, and your mechanical efficiency. So if I try to multiply all the efficiencies, I'll get it. Or theoretically, by definition, if you try to understand what is overall efficiency, it is energy that is available at the end of that particular, what it goes to the generator or something that is available at the shaft, to the energy that is available or energy that is supplied to the fluid. Okay. Now, see, there are such things. We are trying to solve the numericals on your Pelton wheel. Okay. Now, when you are solving this numerical, there are certain things which may be given in the problem statement that we need to understand. So we call that as design parameters of the Pelton wheel. Design parameters. Pelton wheel. Pelton wheel. So what is this actually? The fluid jet velocity. What is it actually? This is the velocity that is coming out of your nozzle. That is V1. Okay. If you go back and see in the fluid mechanics, actually, V1 is given by CV into root 2GH. Okay. What is this H actually? H is the net head under which your turbine is working. Okay. So CV is the coefficient of velocity of your nozzle. So that means whatever it is. For the CV, modifies kind of discharge to your turbine or whatever it may be. So that is given by Q. So usually what we try to do here, we try to express by N into A into V. Where what is your A? A is the cross-sectional area. See, where A is the cross-sectional area of the jet not the cross-sectional area of the wheel. It is the cross-section area of the jet. It is a jet actually. Then what is your V? So this is your jet velocity. What is your V? So this is your actually V1. So it is the jet velocity. V is the or V what we call, that is your jet velocity. Then what is your N? N is the number of jets. So N is the number of jets. So if it is 1, it will be simple A into V1. If it is 2, it is 2 into area into velocity. So that's how you people can find your discharge. So discharge for a 4 nozzles is 4 times your area into V. If I have 2 nozzles, it will be 2 times your area into velocity. If I have, usually there will be U1 number. So either 2, 4, 6, 8, whatever it is. That's how the nozzles will work. Okay. Now the third, what we have to look at is actually is your blade speed or your peripheral speed. Okay, peripheral speed or blade or vane speed, which is given by U is equal to pi into D into N divided by 60. What is this D? So D in N is the speed. See, D is nothing but mean diameter. Mean wheel. And N is the speed in RPM. If it is an RPS, this will be just simply pi dn. You have to be very careful. Sometimes in some of the numericals, N will be given in RPS. So in that case, you should not put divided by 60. If it is N is in RPM, I have to use pi dn by 60. If N is in RPS, I have to use just simply use pi dn. Next, 2 more things. One is the jet speed or jet ratio. We call the jet ratio, which is thing. So jet ratio, okay, and by M, which is the mean diameter of the wheel. See, this is my mean dia of the wheel. So in that case, I will change this thing also. I will put capital D, so it will be easy for you to understand. So this is capital D is your mean diameter of the wheel, and small d is your jet diameter. So it will be easy for us to remember. So capital D is your mean diameter of the wheel, and small d is the diameter of the jet. Okay. What is the number of buckets or number of vanes? Okay. Number of buckets or vanes of the Pelton wheel. So we have a simple formula which is given by Z is equal to jet ratio by 2 plus 15. So 15 is a default number. What is your M actually? It is D by D. So D by 2D plus 15. So this is a simple formula. So that means your 15 is a fixed number. 15 is a fixed number for your Pelton. So at least any Pelton wheel we take, the Pelton wheel should have 15 number of buckets or vanes. Okay. Now, regarding the dimensions of your bucket. Okay, regarding the dimensions of your bucket. So as I told, so if suppose this is the wheel, so this is your bucket. Okay, this is your bucket. It will be something like this. Okay, so something like this. And then, now if you try to see from this end, okay, so then this is your thickness. See from the front, if you see, this is your thickness of the bucket. Now what will happen if you see from this and side view? The side view, if you look at it actually, the side view I will be getting something like this actually. You will be getting almost 2 ellipses actually. It will be like this. You can see this in your, if you come to our lab, no, we have this kind of a dimension. Okay, this is how your, so now what is this actually? This particular thing, this is your splitter. This is your splitter. Okay. Now let us try to put the dimensions. So this will be your length L, and this will be your width B or W, whatever it may be. This is your width. Okay. This is your width. Let me call it as B or W, doesn't matter. It's just a sign convention. Now let me write it. So L is the length of the vane or bucket, length of the bucket. Then B is the width of the bucket, width of the bucket or vane. Okay, then T is the thickness of the bucket, thickness of the bucket. So from the design data handbook, whatever it may be, okay, it has been found there is some ballpark number under which I can easily, if I know the diameter of the jet, see all the values of L, B and T can be easily found if I know the diameter of the jet. So if suppose, see, this is a formula what they use actually. L is varying from 2.3 times the diameter of the jet to 2.8 times diameter of the jet. Okay. Then B is equal to 2.8 times the diameter of the D to 3.2 times the diameter of the D. Then thickness T is equal to 0.6 times diameter of the jet to 0.9 times diameter of the D, where D is the diameter of the jet. You have to be very careful here actually. I have seen many of the students, instead of putting the jet diameter, they try to put the diameter of the wheel. So then your length, breadth and thickness will get a bigger number. So you have to be very careful in putting it. So you can say, for example, if L is length is, you can take 2.5 times D. So some one number you try to remember. So your width is 3 times your D and thickness is around 0.75 or 0.7 times. So need not remember this part. So 1 point, nothing is given here. Fine. So this is about your Pelton wheel. Okay. This is about your Pelton wheel. Now, what will happen if there is a something like I have a reaction turbine. Okay. So if I have a reaction turbine, how my reaction turbine will behave? I'll show that 1 minute. I'll stop recording here because this is with respect to Pelton wheel.